This episode is on differentiation. But first, let's recap line graphs. More specifically, finding the gradient. It's fairly simple. You change in y and divide it by the change in x. But what if the line isn't straight? Well, that's where it gets more complicated. When a line is curved, the amount that goes up by changes. So we can't work out a gradient for the entire line. So, what can we do instead? Well, first, let's think about what the gradient actually is. You may know that when plotting a distance time graph, you could take the gradient to find the speed. This works because the formulae match up. Speed is distance over time, and the gradient is y over x. In a distance time graph, y is distance and x is time. However, speed can also be said to be the rate of change of distance, a number to show how quickly the distance changes. We could say a similar thing about the gradient. It's a measure of how quickly the line is going up or down, but instead of changing over time, it's changing as we move along the x-axis. So, surely we can measure the rate at which the gradient is changing, and we can, through differentiation. Now, there's two ways to do it. There's the complicated way, and then there's the simpler way. The complicated way is differentiation from first principles, and the only time that you have to use it is when the question asks you to. But this is the first one that's taught, and it lets you know why the easier method works. So I'll go through that one first. What we have here is our triangle. That symbol that's not a letter is a delta, and it means the difference in two values. For example, if the coordinates of P are x and y, then the coordinates of Q are x plus delta x and y plus delta y. You'll see that this doesn't accurately represent the gradient of P, so that we use what's called a limit. What we're essentially doing is moving Q closer and closer to P in order to get our value for the gradient, delta y by delta x, as close to the gradient of the tangent at P as possible, as the tangent is the line that has the same gradient as the curved line does at P. Now, because the coordinates of these points are as follows, and the y coordinates correspond to some function of the x coordinate, then we can rewrite our equation. The reason why the fraction has that complicated numerator is because f of x plus delta x will give us y plus delta y, but we only want delta y, so we have to subtract y from it, and y can also be written as f of x. Which is great and all, but what does it mean? Well, first we need the equation of the line, f of x. Say, for example, that it's x squared. In that case, we can put x plus delta x through, and that will give us x plus delta x all squared, and putting x through it gives us x squared, which is pretty self-explanatory. The next step is to expand those brackets. And once we've done that, we can cancel those x squared terms, and then divide by delta x. You'll always be able to divide by delta x, that's by design. And because delta x is getting closer and closer to 0, eventually it will be 0, which means that our expression is 2x. If you're wondering why we didn't make delta x 0 before, that's because we would then have been dividing by 0, which, kind of breaks the whole equation. So, now we can move on to the simpler way. Now, it still will look complicated, but once you've got your head around it, you can basically do it without thinking. But first, let's think about it. The example I'm using looks complicated, but the method isn't. These numbers are just chosen because they're a little harder to deal with, but will help to explain it better. The first thing we're going to do is add x to the power of 0 here. It doesn't do anything because x to the power of 0 is 1, but it's helpful to show. We're going to add a power of 1 here for the same reason. Doesn't do anything, but it makes it make sense. The way we differentiate is using this formula. If we apply that to each term in our expression, we get this. Now, we simplify the powers, which gives us that. And then immediately there are some things we can do here. The power of 1 can be ignored, and the power of 0 allows us to eliminate x. Now, we have a power of x to the minus 1, but don't worry, because once we multiply out those brackets, that just becomes 0, and we are left with our derivative, dy by dx, which is kind of similar to delta y by delta x, but you can tell that this is the one we're going to be using a lot because it doesn't have any Greek letters in it. Now, yes, because that is 0, we can ignore it. In fact, anytime you have a constant like we had our 4 there, it disappears when we differentiate. Now, we can also have other quick methods that we can do, where if we have something multiplied by x, then when we differentiate it, we'll get b. For example, when we had 3x, that went to 3. You'll also notice something else. Our half x squared term became just x. This is another thing that you can look out for. Now, you may realize that dy by dx usually gives us another equation. In this case, we can find out the gradient of a line at any point by plugging in the x value. But if dy by dx just gives us a value, then that is the gradient for the whole line, which means that it's a straight line, and what we've done is just found the gradient, so dy by dx is just y by x in that case. But using the idea of finding the gradient at a point, we can start talking about tangents. Remember, tangents are these things. They cross the line at a single point. We already know how to generate one part of the equation, the gradient. When we've been finding the gradient at a specific point, we've also been finding the gradient of the tangent at that point. So to find that, we just use dy by dx at the point that we're taking a tangent of. The other important part of a line equation is the y-intercept, or c. To do this, plug in the y and x values of the point into the standard equation, y equals mx plus c, and you'll end up getting a value for c, because we know everything except c in that equation. The reason why this works is because the point that we're taking a tangent of is the coordinates to satisfy both the curve and the line. Now, we can also find the equation of the normal to the line. Normals are essentially the inverse of tangents, and they look like this. It's essentially a 90-degree rotation of where the tangent was, and the way we find the equation of it is as follows. To get the gradient, we take the negative reciprocal of the gradient we worked out before, which amounts to doing 1 divided by it and then changing the sign. To find out the intercept, we use the same method from before, but you will receive a different intercept from your normal as your tangent. If you saw that our tangent intersected the y-axis in the negative end because it started low down and then went up, but our normal started high up and then went down. This covers everything that I wanted to put in this video because I'm saving second differential and stationary points for another video, so look out for that when it arrives.